Either we're going to have a look at the requirements for supplementary protective equipotential bonding within your installations. If you open up your regs book to part 4, chapter 41, 415.2 there, we have additional protection, supplementary protective equipotential bonding. If you look at note 1, it's telling you obviously that it's an addition to fault protection. And in note 2, that it doesn't exclude the need to disconnect the supply for other reasons. For example, for protection against fire, thermal stresses, etc. And then they're saying it may involve the entire installation, a part of the installation, even just an item of equipment or a particular location. And in note 4, it's telling you to look at part 7, for example, bathrooms, swimming pools, medical locations, where there are different requirements for supplementary protective equipotential bonding. For example, in certain medical locations, your touch voltage, your maximum touch voltage will reduce. Okay, so we have 415.2.1. Supplementary protective equipotential bonding shall include all simultaneously accessible exposed conductive parts of fixed equipment and extraneous conductive parts, including where practicable the main metallic reinforcement of constructional reinforced concrete. So we're looking to ensure that the potential difference between our electrical installation and any metalwork that might be introduced in a local earth potential doesn't rise to a point where someone could potentially receive a fatal electric shock. Okay, so that might be because of a fault in our installation, or potentially might be issues external to the installation. For example, divergent neutral conductor currents, where we'll get circulating, importing, exporting currents around about the earth path. So we need to ensure that any potential difference between our electrical installation and the non-electrical installation that is within arm's reach is kept to a value low enough that, as I say, that we're not going to result in an electric shock. So we have this last wee section here where it says supplementary protective equipotential bonding systems shall be connected to the protective conductors of all equipment, including those of socket outlets. Okay, so we also consider it from socket outlets as well, not just from fixed equipment as it says at the start. So the next regulation, 41522, was originally worded as you can see back in the 16th edition when it first came out, but in Amendment 2 it changed to where doubt exists in the effectiveness of the supplementary protective equipotential bonding, the resistance R between simultaneously accessible exposed conductive parts and extraneous conductive parts shall fulfill the following. So in 2018 they removed that doubt exists. So for the best part of 24 years, we ran with where doubt exists when it came to testing for supplementary protective equipotential bonding. Okay, now as a result, not a lot of supplementary protective equipotential bonding actually gets tested out there in the real world. So it has been reconstituted back to its original version. Okay, so where we have the resistance R between simultaneously accessible exposed conductive parts and extraneous conductive parts shall fulfill the following condition. So we've got R is less than 50 volts divided by IA for AC systems and 120 volts divided by IA in DC systems. The voltage shown, folks, is the maximum touch voltage that you're allowed between your electrical installation and your non-electrical installation. Okay, so 50 volts AC. Okay, if you look at the information that's there, it's just an Ohm's law calculation. So we have that 50 volts max touch voltage for an AC system. Obviously for a DC system it's 120 volts. Now I prefer, rather than R is going to be less than or equal to, I prefer R max. We're all comfortable using air fault loop impedance tables where we have a maximum air fault loop impedance. This should be no different. Okay, so R max is equal to 50 volts divided by IA. Now, where IA is the operating current in amperes of the protective device, or if we've got RCDs, we use the trip current rating I delta N. So for example, it's a 30 milliamp RCD, we use 0.03 amps. Now it's important that you're aware that the RCDs operate quicker than and at lower fault currents than what an overcurrent protected device does. Okay, so where we've got an RCD and an overcurrent protected device in line with each other, the RCD should operate first before the overcurrent protective device. Okay, because it will notice the imbalance faster than the circuit breaker or the fuse, or it should. We then have point 2 there. For overcurrent protected devices, we use the 5-second operating current. Now, the 5-second operating current we find in Appendix 3, pages 411 to 419. So we have a real-world example here. We have measured between this switch and this worktop here on the continuity setting on our meter after 0 and our leads. We've measured a resistance of 1.71 ohms between this switch and this worktop. Okay, just a continuity test. 1.71 ohms. Upon further investigation, we identify that the circuit there is protected by a 20 amp type B MCB. Okay, so if you get into your regulations book and you go into your index and you go to supplementary protective equipotential bonding, you'll see there that the first point underneath that heading is additional protection by, and it's sending us to 415.2. Okay. When we go to 415.2, we're back to that regulation that we just looked at. Now, as I said, the operating current for the devices is for the 5-second operating current. Okay. From Appendix 3, pages 411 to 419. Now, we are looking for a 20 amp type BMCB, so we find that on page 417, figure 3A4, and you'll see there at the top there it's got the type B MCB, and we've got our British standard there. Okay. Now, we could use the time current characteristics, we could use a graph, but however, we're looking for the 5-second operating current, so we are going to use this table here because you'll see that it's got 5 seconds there identified in the table. Okay, so looking at the table, it's a 20 amp type B MCB, therefore the operating current is 100 amperes, 5 times the rating. Remember, type B circuit breakers is 5 times, type C 10 times, type D 20 times for the 0.4 a second, but for the 5 seconds it's 10 times, so it's got the same time current characteristics as the type C device. Okay, so we take that information and we write that information down. So it's a type AC supply, 50 volts AC is our maximum touch voltage, and our operating current is 100 amps, so we need to work out our maximum resistance that we're allowed between these 2 points. So we take that information and we throw it into our Ohm's law calculation. So R max equals 50 volts divided by that 100 amperes. So that's the maximum touch voltage divided by the fault current at 5 seconds. So that gives us a max resistance there of 0.5 of an ohm. Okay. Remember, our measured value was 1.71 ohms. Max 0.5, measured 1.71. We clearly have a measured value higher than the maximum that we're allowed, therefore we need to fit bonding. Okay, if I did not fit bonding, if I take this 1.71 ohms and I multiply it by 100 amps, I would get 171 volts between this exposed and this extraneous conductive part in the event of a fault. Okay, and that's why it's dangerous. All right. So what if we had a 30 milliamp RCD in line with this circuit? Would it change the maximum resistance allowed? Well, we're going to take that 30 milliamps and we're going to throw it into the same calculation. Remember, it's 30 milliamps, it's not 30 amps, it's 0.03 amperes. So that gives us a maximum resistance of 1,667 ohms. We measured 1.71 ohms, therefore bonding is not required. If we had a 16 amp BS88-3 cartridge fuse in front of this circuit, we would then need to go, rather than going into page 417, we need to go to page 411, figure 3A1, where we've got our BS88-3 fuses. And again, what we're interested in here is this N column here in the table. Okay, so in the table, it's a 16 amp device. okay, and that says we've got 56 amperes is going to flow in order to operate that device in 5 seconds. So we take that information, same information, and we throw it into our calculation, Ohm's law calc. So 50 volts max touch voltage divided by the 56 amperes, which is a 5-second operating current. That gives us 0.89 of an ohm, okay? Remember, our maximum measured from earlier is 1.71 ohms, therefore we're clearly higher than the 0.89 ohms max, therefore bonding is required. If I was to take that 1.71 ohms and multiply it by 56 amperes, I would get roughly 96 volts of a potential difference between our exposed and our extraneous conductive parts, okay? Again, potentially dangerous, above that maximum 50 volts. Now, depending on the installations that you work on, you'll see that I've got all of the fuses. If you work on installations where it's predominantly fuses that you are working on, go down that 5-second column for every device that you regularly work in and work out your maximum resistance between your exposed and your extraneous conductive parts and make yourself up a wee table. Okay, you could do the same for circuit breakers. Go down your column for the devices that you normally use and make up your own tables. Okay, remember, practice, practice, practice. That's how you get good at these types of calculations. Again, remember, if this comes up in your exam, it's only an Ohm's law calculation. Okay, so hopefully this will help you. Remember, if you need to, go back, rewatch it, pause the video, try the calculation yourself. Okay, so good luck moving forward, folks.